Bienvenue au Colloquium. It's my pleasure to introduce Kathryn Mann from Bowden, who will speak on rigidity from infinity. Please.
Bonjour à toutes et à tous. C'est un plaisir de vous présenter un peu de mes travaux. Je comprends, il fait très chaud ici, mais j'ai entendu dire qu'il y aura un pot juste après avec des boissons très frais. Alors, okay, but I will give my talk in English because my slides are in English, and it'll go better that way. The goal, rather than present in detail one piece of work, I want to present to you a broad theme that has influenced my work for several years and has echoes throughout a lot of different areas of math. Okay. So what's the title? Rigidity from infinity. The suggestion is that, as in this picture, you have a group acting on some kind of space. So here, I have a picture of a nice tiling of the pointary disk model of hyperbolic space, maybe familiar to many of you. And if you move the sides by these arrows, you do this transformation, you get a nice GS2 surface. So I really have the fundamental group of a surface acting illustrated here. And the idea is that, well, I have a circle here compactifying the space, and by understanding what happens at infinity of that circle, I can recover important properties of the action. That kind of idea, in many contexts, is what I want to unfold throughout the talk. Okay, so let's start at the beginning. The broad theme here is to find examples of dynamical systems that are stable under perturbation. Stable or rigid, I'll use these words almost interchangeably. For the purposes of my talk, whether one word is used to the other, it's usually just historical accident, or one sounded better. One says Moscow rigidity, but Sullivan's structural stability. Right. A dynamical system for me is classically one considers either a single transformation under iteration or a flow, a one parameter family of transformations. The more modern interpretation is you have not one transformation, but several transformations of a space that interact, and they satisfy some laws. And so that gives you a group structure. And an action of that group on the space is just a representation of the group. My abstract group will always be gamma, to the group of homeomorphisms of that space. And to be stable under perturbation means that if I change it a little bit, what does that mean? I take a new representation that is nearby in the compact open topology on the space of all actions of my group on the space. But you can really just think that I've perturbed what, say, the generators of my group do if it's finitely generated. If I perturb it a little bit and it has the same behavior no matter my small perturbation, I would say that's stable. Well, I'll unpack that in a second, but I want to motivate this general problem first. This is the only problem I can ever motivate to non-mathematicians. Because if you want to, measure something in the actual physical universe, or if you want to numerically model a system of transformations, right, you can only do that with finite precision. And so the question is, well, was your finite precision good enough? And if you were modeling something that you knew a priori to be stable under perturbation, well then the long-term outcome is not going to be so sensitive to the initial conditions, and your rounding error will make a huge difference. Okay, so that means we'd like to know a priori what kind of dynamical systems are stable under perturbation. And well, I don't do applied math, so for me, I just want to go to the toy box and play with the most simple toys to try and identify some phenomena that gives rise to this stable behavior. Okay, so let's go to the toy box and play with some mathematical toys. Okay, so here's a very baby example of a group acting on a space. My group is an infinite cyclic group. It's just iterates of a single transformation F. And my space is the simplest possible space, perhaps. It's the closed interval. Okay, and here's my action. I drew, it's a function, right? From the interval to itself, I drew a graph of a homeomorphism. Sometimes it's more helpful to illustrate it this way, right? Here's my interval, and the arrows represent what direction points move under iteration. Okay, so if I iterate this function, everything gets sucked into this fixed point. Okay, let me perturb this a bit. To take a nearby action, that just means I take a homeomorphism whose graph is pointwise close, right, so close to the graph of this one. So let me do this, and you'll notice you can prove that you can give it to your most beginning student, right? If I take something nearby, it will still have at least one fixed point. So the property of having fixed points in this example is stable under perturbation. But of course, you might end up with many fixed points. Here in my example there, I ended up with perhaps a whole interval's worth, or maybe it wasn't an interval. You zoom in, my line is even more wiggly. Maybe it's not even differentiable anymore. You can find a Cantor stat worth of fixed points or some crazy behavior, but they'll all stay near the original. Okay, so existence of fixed points is a stable phenomenon, but the number is not. If you required some regularity, not acting by homeomorphisms, but by diffeomorphisms, and you required your perturbation to be C1 close, meaning that not only was it pointwise close, but the derivatives at every point were close to the derivatives of the original function, then you will retain this kind of behavior. You'll have a unique fixed point. That's also an easy calculus exercise. And so the result would have the same kind of coding picture, and it would be conjugate by some change of coordinates, typically not differentiable, but conjugate by some homeomorphism to the original code. So in the C1 perturbations land, one often sees stability to mean under a small perturbation, the result is conjugate. If you care about actions by homeomorphisms, this type of behavior occurs. And if I want to turn this back into this, I need to collapse that whole bunch of fixed points or garbage that I got. This motivates the following definition. A group acting on a manifold is C0 or topologically stable if any nearby action, any small perturbation, is semi-conjugate to it. Not conjugate, but semi-conjugate. And semi-conjugate means exactly this kind of collapsing behavior. The two are related. So there's a continuous surjective map from your space to itself that intertwines the two actions. My original one sits on the bottom. It has the less complicated behavior. And my perturbation sits on top. And there's some map that collapses the perturbation down to the original. You'll notice this definition is not, with the notion of being semi-conjugate is not symmetric. Right? H goes one way, it doesn't have to be invertible. But what it's saying is that the perturbation is at least as complicated as the original system. So notions that measure complexity, like entropy of individual elements, they can only go up. Maybe a more basic notion of complexity is how big is the kernel of your action, right? If I perturb rho naught and I get something semi-conjugate, I don't have bigger kernel. Anything that acts trivially here, well, down here it's acting trivially as well. Okay, so this is the type of stability that's going to come up in most of the talk, because I'll consider actions by homeomorphisms. But I want to give some historical context where we have much more regularity. So I mentioned before, kind of the beginning of dynamical systems was for iterations of a single element rather than a complicated group. The story of really the rich modern history of the study of group actions begins in a much more algebraic context where your groups are lattices and loop groups. So let me talk a little bit about how this all got started. A lattice is just a group with a discrete group with an interesting structure, a discrete group of a Lie group that retains some memory of the group it was in, meaning that the quotient should be finite volume. And we call it co-compact if the quotient is compact. So the examples to keep in mind are take something like SLNZ and SLNR, that one's finite volume but not co-compact. If I have some kind of manifold, this is only interesting if it has a geometric structure, it has some kind of homogeneity to it. The universal cover, the isometry group of the universal cover is some kind of the group. And oops, there's a one missing from my pi one. The fundamental group of my manifold acts on the universal cover by Beck transformations. If I have lifted the metric off of my manifold, well, then I see it as a discrete subgroup of isometries. And if my manifold is finite volume or compact, I'll have finite volume of co-compact quotient. Here's a theorem which you can cite as maybe the starting point of rigidity of lattices. It's a rigidity theorem in the algebraic setting. We did Selberg, 1960. If you put a co-compact lattice in SLNR, then it has a rigidity property in the algebraic sense. If you take a nearby representation, something nearby to the standard inclusion, the only thing that you could have done was conjugate it, and actually conjugate it by some element of SLNR close to the identity. So deformations of this come from conjugation. This led to a whole host of generalizations of the study of rigidity of lattices in Lie groups, Calabi, Mostow, Prasad, global and local results, and in many different Lie groups that behave somewhat like SLNR does. Since this is not the point of my talk, I'll not go deep into what that means. But instead, I'll pass specifically to Mostow's version, and actually what Mostow had to say about Selberg. Mostow was so inspired by this particular theorem that he wrote a whole survey paper talking about how much he loved it. And here's a quote on what he reads out of Selberg's proof. Mostow writes, upon analyzing Selberg's proof of his rigidity theorem, the one I just quoted, the key relation shows its force as certain sequences of elements go to infinity. Doesn't matter what this thing means. In Selberg's proof, these happen to lie in some abelian subgroup, which explains the next sentence of Mostow. It says, well, since your Lie group itself is not abelian, I thought, it seemed to me that desirable to exploit relations at infinity, not only on abelian subfamilies, but among all elements of gamma, your lattice, near infinity. But what does infinity mean? So Mostow reads Selberg's proof. He sees inside a bunch of algebra some geometric idea that you should look at what's happening at infinity. And here's the picture that kind of comes out of it. So my cartoon will be the setting that Mostow originally proves a very strong rigidity result in. Considers lattices in SO1, same thing, which is the isometry group of a hyperbolic space. Here's a nice cartoon proof of or at least an outline of a beautiful theorem in mathematics. And my goal here is really to just present to you the outline, nothing of the details. So here's the outline. If I happen to have isomorphism of lattices, so I'm thinking of gamma 1 as my usual inclusion and gamma 2 is a small perturbation. But in fact, in the end, you can do much more. Okay. So I can translate this into equivariant map on the hyperbolic spaces in which these were lattices in the isometry. So here I've cartooned this picture in the only setting where you actually have real actual deformations where n equals 2. But the cartoon is representative of all situations. And so there I had my lattice. Here you can think of it like my first slide. I'm an algebra of a surface, and here I have some different versions. The fundamental domain is a different shape, so I deformed it. These are the same kind of things, so you can sort of see this isomorphism geometrically in this picture. And the look to infinity step of the proof is to show that this map extends to a homeomorphism on the boundary spheres of hyperbolic space. In this case, it's just a continuous, or actually a homeomorphism from the circle to the circle, equivariant with the respect to these actions. And then the hard part of the proof, the really key step, is to show that this boundary map, what happens at infinity, has some kind of regularity. And then to improve that regularity, to actually, it came from an isometry of the space, and my two things were related by conjugation by some element of my computer. Okay, what is this regularity? Moscow's version is that these boundary maps are quasi-conformal. That's actually not so hard to do by hand. And the improvement is you use there is some, in his version, some ergodic theory and analysis to figure out that they're actually forced to be conformal. And there's many other versions of this final step of improving regularity rather than using ergodicity arguments. There's a sort of a Thurston Gromov version that uses volume of simplices. There's a beautiful, much more recent recasting of this proof by Courtois and Gallo. Gilles not here, but it's the best proof, where they just kind of build this isometry by best for some reason. It's the simplest. Okay, so what does this whole picture suggest? It suggests that, I don't know, maybe there's a general practice of looking at boundary maps to recover some rigidity properties of a group acting on a space. And what did we do here? We improved some kind of homeomorphism of a boundary into an isomorphism. Okay. Well, since Moscow, there are many results on rigidity of lattices generalizing this theme, typically acting on spaces by diffeomorphisms or by putting lattices inside different Lie groups. You were originally a lattice in G, and now I'm going to put you inside of some bigger Lie group and talk about the deformation space in there. And the general tools for these span typically techniques from differential or smooth dynamics, or homogeneous dynamics, the study of symmetric spaces of Lie groups, basically. In the setting where you just have actions by homeomorphisms, C0 actions, there's very few tools that apply, and not so much action historically. And the point of my talk, for the rest of the talk, I want to talk exactly about this big question mark, this C0 setting, in three contexts that are all important in their own right, and where we've made some progress. So these are first the context of super low dimension, because of its relation with some algebraic structures, orderable groups, and boundary cohomology. The second is a generalization of this idea of a boundary of hyperbolic space to a boundary of a purely algebraic object, the Gromov hyperbolic group, which has connections to geometric group theory. And the third is a recent project that we're working on that kind of goes back to classical dynamical systems, understanding Anosov flows, very rich dynamical systems on free manifolds. And in all three cases, the point is to recover some surprising stability or rigidity from a kind of Moscowian perspective of looking out to infinity. Okay, and historical overview. And let's commence some three specific settings. Okay, first is dimension one. Ignore my slide except for the first sentence, which is, here's a big problem, right? You give me your favorite group, this finitely generated group, say, and your favorite space, maybe it's a manifold, two-sphere, whatever you want. Can you describe all possible actions of the group on the space? And unless your group was finite, the answer is no, in basically every situation ever, unless your manifold is one-dimensional, in which case we have some tools to answer this extremely hard problem. Okay, so I'm going to replace M by the circle, because this is still an interesting question, and talk about how we answer it through various groups. Okay, so the first question you should ask is the existence question. Is the set of all actions of my group on the circle empty or non-empty? Right, I guess you always have the trivial action. Okay, but let's use the actual group and ask, is there a fateful action of the group? This is a question that is undecidable in general, but it's semi-decidable in a very computable sense. Namely, in theory, if you know all of the elements of your group, if you have some good way of describing the group to a computer, there is an algorithm that will run, and if your group has no fateful action on the circle, that it will output no in finite time. And if your group does, it'll just keep running forever. This is not completely abstract. In the case where you replace the circle with the line, this has actually been implemented and has, there's a particular implementation done by Danny Caligari and Nathan Dunfield. They were interested in various structures on three manifolds that they reduced to a question about the fundamental group of that three manifold acting on the line, yes or no. And they got a computer to output no for a hyperbolic manifold they were particularly interested in, and that was a theorem. It was the first example of something that lacked this structure. Okay. Okay, great. So at least maybe you're satisfied that the existence question is something sort of approachable in this case. Right. So now we've pretended we can answer the existence question. Now we want to describe all possible actions. This is also sort of a thing you can code somewhat algebraically in the second bounded group cohomology of your group integer coefficients. You don't need to know exactly what that is. It mimics ordinary group cohomology. It's functions from tuples of elements of your group that in the integers modulo some co-boundaries. So I will give you an explicit cocycle that tells you about actions. If you have an action of your group on the circle, then I can define a function that takes a triple of elements and outputs an integer, either 1 or -1 or 0. And what is that? I fix something to be my base point, x, not drawn here because it doesn't matter. And I look at its image under gamma 1, gamma 2, and gamma 3. And I will say 1 if it's sort of the usual orientation on the circle as I read them in order. -1 if, say, gamma 2 is over here instead, I would read -1. And 0 if something's degenerate, say gamma 1 equals gamma 2. It's really just giving the orientation of this triple of points. Wait, why is this a 2 cocycle? I had 3 inputs. You'll notice if my group preserves orientation of the circle, then this output is invariant under left multiplication. I multiply all my inputs by, I don't know, gamma 1 inverse. You put the identity there, and I really just have two inputs. So it's something that really secretly depends only on 2 inputs. It satisfies a cocycle condition on 4 tuples. If I take a fourth element, gamma 4, and maybe gamma 4 of x is down there. There's some relation between all the possible 1, 2, 3s, and 4s that I could substitute in. And if you want to try and work out what that relationship is, I've drawn a cartoon that really looks like what is it? 3 things give me a triangle, but there's 4 give me lots of triangles. And this, if you think of it as a 3-dimensional picture, it looks like a simplex, right? Like a 3-dimensional simplex that I've splashed down on here. Okay. And that's the hint of why you should think of a 4 tuple as having some kind of boundary relation. I've drawn actually a bunch of faces of a simplex. Okay, so that's a way that given an action, I can describe, I don't know, a function on triples of my group that satisfies some cocycle condition. If I want to simplify my life, it's a worse formula to write down, but you can just believe me that there exists something homologous to it that actually only takes 2 values. You don't need +1, -1, and 0. You can actually get equivalent information just with 2 values. And FNG showed that actually this machinery is exactly describing all possible actions of a group on the circle. Okay. So elements of second bounded cohomology, these types of functions, modulo coboundaries that emit co-cycle representatives taking only the values of 0 and 1, are in one-to-one correspondence of actions of your group on the circle up to semi-conjugacy, that relation I had on my first slide where you're allowed to collapse down intervals in some kind of equivariant way. It's also capturing the space of all actions of the group, well, up to something, the equivalence relation generated by semi-conjugacy. And this up to something actually turns out is the way you turn the space of all actions into a reasonable space. The space of all actions with its natural topologies is horrible, but given a horrible space, there exists by abstract topology a largest Hausdorff quotient of that space. So if you collapse all the non-separable points, right, the things that can't be separated by open sets, you declare to kind of be the same. If you pass to the Hausdorff quotient, you get exactly actions up to semi-conjugacy. Think of this Hausdorff quotient is, the things that you can detect being different by continuous functions, right, by things you can actually do. Okay, great. So what is this telling us? If you have a group and you want to understand all of its actions on a manifold, there's a sort of system or some machinery for doing this, provided your manifold is a circle. And of course, the next question is like, well, okay, let's put this in practice. Are there some gamma that give me some interesting example? All right. Well, let's try and figure out, maybe there's some gamma lattices with circles at infinity, and I can apply the Moscow machine, this philosophy of my cock to it. Okay, well, actually, I'm quite restricted in that sense. If you have a space associated to your Lie group where the boundary happens to be a circle, well, then your Lie group was SO21, the isometries of the hyperbolic plane, and your lattice up to passing to a finite index subgroup was the fundamental group of a surface. And we're already kind of dead because this is the one dimension, the one setting in which Moscow rigidity fails. On the previous slide, there was a little like provided n bigger than 2. Here's the part where it's no good. The end of that, what goes wrong is the end of the proof, the boundary map, the map from boundary circle to boundary circle, which you were trying to show has some regularity. Here it has no regularity. And in fact, there's typically it's what is it? If it's different, it's like it's not differentiable at a single point with non-zero derivatives. It'll have derivatives almost everywhere by some quasi-symmetry argument, but they'll be basically 0. And not differentiable everywhere. And instead, there's a 6G minus 6G is the genus of your surface dimensional space of deformations of inclusions of your group gamma into this group. You can make actually an entire career out of just studying this space and be very well paid for it. Okay, so bad news. But maybe the question is, if I am not concerned about staying inside a Lie group and understanding conjugacy in my Lie group, maybe I could recover some rigidity. And in fact, I do. So Matsumoto showed in 1990 that this kind of boundary action, the action of a surface group on the circle, as you move through your Lie group, you're no longer conjugate in your Lie group, but you're always conjugate by some homeomorphism. And if I take my actions not to just lie in a Lie group, but just to be actions by homeomorphisms, well, there's still no deformations. So this is the first example, the first, like, to me, I guess, very, very interesting example of a boundary action that has C0 or topological stability, a sense I defined at the very beginning. not just a local version here. Also, Matsumoto's theorem says that it's almost global. There is an entire connected component. So you can imagine deforming this action along a very long path. You keep changing it, you keep changing it, you keep changing it. Oh, theorem, you didn't change it at all. The end of your path is still semi-conjugate to the original. And encodes all the same information. You didn't meaningfully change the dynamics. So this theorem has been an inspiration to me for a long time as a good example of C0 stability. And in joint work with Maxime Wolf here from the parallel hallway, we showed that there was almost a converse to this theorem. Namely, these boundary actions are the only rigid examples of surface groups acting on the circle. You happen to have a connected component of this space that's one single semi-conjugacy class. Everyone's semi-conjugate to some model. You can read this sentence as saying there exists some representation so that no matter how you deform it, it's only by semi-conjugacy. Well, then that was the class of the standard boundary action. Your model was the standard action of this surface group on its boundary. Or wait, there's one silly thing you can do. The circle happens to be a cover of itself, degree k for any k. And for many examples of k, you can list these actions. You know exactly when. And those behave dynamically very much the same way. So these also give rigid examples, similar in Matsumoto's theorem. And okay, actually, permitting lifts to covers gives you all rigid examples. So this was a big, long piece of work that took us many years. But the upshot is that we can describe many components of the space of all actions of a group on a manifold, something that has been done in very few contexts. We have a classification of all stable or all rigid actions. And the proof idea is something I want to share a very small cartoon of. The original inspiration came from, to me at least, you ask Maxime, he'll give you a different answer. But to me, the inspiration for why such a thing might work comes from Dave Gabai's proof of the convergence group theorem. This is a famous theorem in three-manifold topology and surface groups that says that you can identify the action of a surface group on its boundary by some list of dynamical properties. Morally, that's what it says. And his proof somehow considers this action of the boundary and reconstructs sort of the hyperbolic plane on the inside. So we have this kind of reconstruction idea. So let me turn this to you in pictures. So the idea, I'm going to pretend the sentence on lifting the covers didn't exist because that's the hard part. Let's pretend that that was never that the circle didn't cover itself, and so we had a much easier theorem to prove. Okay. The goal is to try and recover the standard action of the surface group or understand the topology of the surface from the action of its fundamental group on the boundary. And you can do this. There is a nice relationship here. So here's my surface, and I've drawn on it three curves. And there's a difference between them on the surface. Namely, the pairs A and B, even if I detach them from their base point and isotope them around, A and B will always intersect each other. I can try and pull B away, but it's always non-trivially linked with A. Right? Versus C, if I detach it from the base point, an isotope that it did, I destroy for both A and B. And this very simple intersection pattern of simple closed curves means that if I choose lifts of these curves to the universal cover of my surface, I will see the curves, the lifts of A and B cross each other, intersect somewhere. I just project out with an intersection point. But see if I take a geodesic representative of it, say, not exactly a lift of this one over here, but a shortest representative, and I lift that, I'll see a curve that's disjoint. And the action of the fundamental group of this surface on its universal cover is exactly what I've cartooned here. These curves, or lift of geodesic representatives, serves as axes. Points get translated along. And the action on the boundary is on the same direction. So here it's drawn just for B. I have two fixed points, and under iteration, this one's a repeller, and that's an attractor. As I iterate B, points will move around like this. So what's the upshot? And forget what's drawn on the inside, and remember how curves on my surface are configured by understanding the location, or who separates pairs of fixed points and who separates who from who. So this is a summary of what's happening on the boundary. Every element of my fundamental group acts with an attractor and a repeller. Right? And A and B being topologically linked curves, even up to isotropy, means exactly that one of the two fixed points of A separate the fixed points of B, versus unlinked, where the fixed points of B do not separate the two fixed points of C. So something about the standard boundary action remembers the topology of the surface. Great, so that's this. And if you take the standard boundary action and you try and deform it, you can think of these in in SO21 if you want, and write down matrix deformations and play with very explicit examples. You try and do the most naive deformation here. The easiest one to write down is to think of your surface as cut it here and use Van Kampen's theorem for groups. It becomes sort of an amalgamated free product. And you discover that you can do an algebraic deformation. You can replace A with the composition of A and something that commutes with B and not change C. The idea is you have, if you're using Van Kampen's theorem, I can sort of do something over to half of my fundamental group without touching the other half, as long as they come together. Okay. So you can do this at deformation, and you'll see the action of A, its fixed points will move a little bit. But if you start from this configuration and you do this very much by hand, they'll never move so far as to interact with the fixed points of C. We tried this, we really did it in SO21 writing down things. It never changes. And the whole philosophy is to show that this exactly characterizes boundary actions. First, if you have an abstract action, you don't know it comes from the boundary, but you know it's rigid, you want to show it comes from this sort of standard action. You do some calculation analysis to argue that rigidity implies, at least for elements that look like this, elements of the fundamental group represented by non-self-intersecting curves, they have some fixed points. You could draw cartoons like this. And you show very carefully that if the configuration happens to differ anywhere from the standard boundary one, like perhaps this B plus was not here, but it was over there, then you can do by hand a deformation exactly like this, an algebraic looking one, that will change the configuration of fixed points. So B plus happened to be over here. Doing exactly this would move A, I'd be able to move it far enough to live with C. And so I guess that's the converse to this, saying that if you're not the boundary action, then you're not rigid. So as the cartoon of the strategy of the proof, it's really playing with configurations of fixed points on the boundary. But of course, the cartoon version is not quite the real one because of this passing to a k-fold cover thing. So this cyclic order of fixed points is really replaced somewhat by dynamics of k-tuples and something that behaves a bit more like a Markov partition type argument. But this is the underlying philosophy. Okay. Since it's late in the day and we're hot, we'll pass to a broader overview set of kind of proof techniques. That kind of toolkit that we developed for this was robust enough to answer a bunch of other questions. So it was a long-standing question of Benson Farb, whether certain mapping class groups had interesting or pathological actions on the circle. So, and the answer that we found was no. If I take a mapping class group, so the mapping class group of a surface is a group of homeomorphisms up to isotropy, or pi naught of a homeomorphism group. Here, the one means that as well as having genus G, my surface has a preferred market point. And we showed using some of this toolkit that actually this group has only one. Here's a group where we can totally describe the space of actions on the circle. It's 2 points, 3 points if you care about the orientation of the circle and you don't allow me to reverse orientation up to semi-conjugacy, the trivial action and a non-trivial one. And the non-trivial one is this group also has a natural action at the boundary of infinity of the universal cover of your surface. The marked point on your surface allows you to pick representative homeomorphisms that fix a marked point somewhere up here. That gives you a canonical list of this group to act on the universal cover that extends to an action on the boundary. So as has long been known, there's a nice action of this group on the circle theorem. It's the only one. Again, with the same kind of toolkit and using some more classical dynamics like Sternberg's linearization theorem, things typically used in smooth dynamics, we're able to answer another basic question, which is, can you differentiate between groups of diffeomorphisms of manifolds just by looking at their finitely generated subgroups? Some kind of can you tell the difference between two very big things by looking at the spectra of small things inside? And the answer for one manifold is yes. You fix a fixed manifold, say it's M is the circle. If you fix 2 different degrees of regularity, there is a finitely generated group of C alpha diffeomorphisms that is not isomorphic to any subgroup of C beta, class C beta. So the regularity of your diffeomorphism group is detected purely by the finitely generated subgroups. So we proved independently using different methods by Kim and Kuberta around the same time, 2019, 2020, 21. I don't know, the pandemic makes it hard recently. Okay, that's the survey of dimension 1. Let's go up in dimension. Dimension not 1. If instead of my surface group and I had my hyperbolic space and I have the boundary at infinity, I could try and just do that in higher dimensions. Take a compact hyperbolic manifold or a Riemannian manifold of strictly negative curvature. You can compactify its universal cover by a sphere at infinity. You can think of this as sort of all the ways of looking out. So what's this compactification in the manifold sense? It really is directions, right? You can think of it as a visual boundary. One precise definition is equivalence classes of geodesic rays. Geodesic is my line of sight, right? If you're standing directly in front of me, we'll both be looking in the same direction. So the geodesic base that my eyes and yours should be the same. Similarly, if I'm in a flat space and I take it one step exactly to the right, I don't change directions, right? Then I'm still facing the same point asymptotically, right? So I would consider this and this be equivalent directions. More generally, you say the boundary compactification of a space, or the Gromov compactification of a space, is equivalence classes of geodesic rays in this metric space. Up to the equivalence relation where you're equivalent if these geodesics stay a bounded distance apart from for all time. That's the right way in metric spaces to think of like visual directions. it's not obvious right away that the fundamental group of your manifold acts on this visual boundary by homeomorphisms. That uses negative curvature. And it applies actually in a much more general setting. You don't need to take manifolds of negative curvature. You can use any space that's of kind of coarse negative curvature. The notion of a hyperbolic group is just a group whose Cayley graph has some resemblance to a hyperbolic space. And in this setting, the same kind of logic goes through. The Cayley graph of such a group can be compactified by some boundary at infinity. That's exactly equivalence classes of geodesic groups. And the definition of hyperbolic is cooked up so that the action of the group on a Cayley graph by left multiplication extends to an action on the boundary by homeomorphism. So a geodesic might not go to a geodesic, but it goes to something close to a unique geodesic. So you can assign it an equivalence class. So here's my example to demystify this concept. Here's my group is a free group of two generators. Drawn its Cayley graph with this generating set. In this direction, in that direction. It's an infinite four valence tree. And the boundary is really just the boundary of this tree, which is homeomorphic to a Cantor set, the space of ends. Geodesics in a tree are just paths that don't backtrack. Right? So every way of going out to the end gives me a boundary. And here, I don't have to worry that action of my group is by automorphisms of this graph. And so geodesics go to exactly the other geodesics. And that's the action of the group on this boundary. Amazingly, we don't know what topological spaces all arise as boundaries of groups. This is a hard and probably never going to be solved problem in geometric group theory. We know many examples. Typically, they look like some kind of Sierpinski carpet or Menger curve or Menger sponge of higher dimensions. If you have manifolds, their fundamental groups always have nice sphere around. Okay. But look, I just discovered a whole huge, big system, interesting class of dynamical systems. I didn't discover it. The dynamics of these have been studied for a long time, of groups acting on topological spaces by homeomorphism. There's no better structure than a topological structure. There's no smooth structure to a boundary of a group. Even if it happens to be the sphere, there's no natural smooth structure, typically invariant by the action. Here's a huge class of groups acting on spaces by homeomorphisms. Guess what? They all are C0 stable. There's a theorem I proved with Jonathan Bowden for fundamental groups a long time ago, or a few years ago, more recently with Jason Manning and Teddy Weisman in the general case. This provides a big class of dynamical systems with the stability property that I was talking about, that I was motivated to find since the beginning. The proof of this theorem, well, actually, before I talk about the proof, I'll make one comment, which is, as I mentioned, we don't know what the boundary is, right? So I'm not actually using anything about this, about knowing exactly what the space is, other than it's abstractly the boundary of a group. That's what was some of the original difficulty. In the case of the fundamental group of a manifold, we know what the boundary is topologically, it's the sphere. That made that a lot easier to do. The techniques we used here were first sort of a kind of a geometry topology version. We tried to capture an action by building a more complicated space, but one where the action was easier to understand. And this is a perspective that's been used by Thurston and Bill Goldman up to present-day use of François Labrie to understand Anosov representations or representations of groups into loops. We did it sort of in this very geometric group theory version. The more recent version uses a symbolic dynamics argument, where we code boundary points by strings in a finite element, a finite set that we take from our group using the dynamics of action. Perhaps this result is not super surprising, or maybe the proof techniques we use are not super surprising, because there's really a long history of studying the dynamics, both in terms of symbolic dynamics and associated species, studying the dynamics of groups acting on their boundaries, going back to Gromov and Sullivan and Canada and Bowden, used in many more recent versions of coatings and of various stability properties in special cases. But to my knowledge, there's no one to sort of ask the most general question that we answered until now. Thank you. To conclude, I want to talk very briefly about project number 3 that uses boundary actions or rigidity of boundary actions to approach a totally different question. So if you take nothing else away from the talk, perhaps you'll take away the point that looking towards infinity can be a relevant and useful tool to prove theorems that you might not expect, things that are not about group actions at all on the surface. So for this little piece of the story, I'm going to talk about a different version of dynamics, which is not actions of discrete groups, but flows. This story starts, or the way I'll tell it, starts in the 1960s with work of Anosov, who was studying the dynamics of geodesic flow in negative curvature. So you take a negatively curved Riemannian manifold, and geodesic flow is a flow on the unit tangent bundle, which takes the tangent vector, and you exponentiate, you get a geodesic, and you just follow this for some time, and you stop in a new tangent vector. Okay. Very simple to define dynamical system, but it has very robust dynamics. In negative curvature, what Anosov discovered is these flows are globally stable. If I perturb them a little bit, I get something which is qualitatively the same, typically conjugate. And in fact, it wasn't something special to geodesic flow. The properties that you need to prove this result, to sort of understand, to generate these rich and yet stable dynamics, were just the fact that there was some kind of transverse expanding and contracting behavior. So exactly the picture here that I've cartooned. So what are these arrows? They are the directions of my flow. And on some kind of invariant plane here, so my picture is in 3 dimensions. I'll pretend I'm on 3 manifolds because that's my intended context. There's locally there are planes consisting of orbits that come together, and a transverse plane consisting of orbits that diverge, or at least in backwards time converge. So you can write this down very formally with a statement that says, well, there's 2 invariant distributions on your tangent bundle. But the topological version is that there's 2 invariant under your flow foliations on your manifold, and on leaves of one orbits converge in forward time, and on leaves of the other orbits converge in backwards time. So this is a local picture everywhere. And flows with, you can also make a good living just studying Anosov flows. These are fascinating examples of dynamical systems because of their tagline is global stability, yet local chaos. So by Anosov's work, if I perturb the whole system, it's conjugate to the system. So I have stability. But if I'm living inside the system, if you and me are both standing inside there, and we get flowed, moved along by the flow, then our trajectories will typically diverge and end up wildly different. Right? So predicting the movement of an individual particle is impossible, but describing the large behavior of the entire system is completely possible. Makes it a very rich thing to study. Okay, great. Rich thing to study. What are all the examples of it? Geodesic flow. There's some things you can kind of build algebraically, and then examples, right, and hopefully classify them. Work of Handel and Thurston and Goodman and Fried and more people up to present day gave techniques to sort of take some building blocks and glue them together and give new examples. Most of these apply only in dimension 3. So we have lots of examples on 3 manifolds. And much more recently, this program more starts in like 2014 here. There were a few examples earlier than that in the 1990s, but the real glut of examples starts in recent years. The constructions tend to change the manifold as you change the flow. You get examples on new manifolds. It was a long question of, could you find lots of examples on a fixed manifold? And the answer finally is yes. We have techniques that if you give me a certain 3 manifold, well, I'm allowed to choose the 3 manifold. I can build you a 3 manifold that has 100 distinct Anosov flows. So it emits many, many different rich dynamical systems. Except I have to tell you what distinct is. What does it mean to be many versus the same? Okay, and so this is the definition. You're the same if your orbits look the same. All right. There's a homeomorphism of your manifold that takes orbits to orbits. How do you tell things are not the same? Well, here's one invariant to tell the 2 flows are not the same. You can look at all of the, well, orbits, what are orbits? They're trajectories. Some of them are closed. You come back to your starting point. Just remember all the closed ones. There's a bunch of loops in your manifold. And I can think of them as 3 homotopy classes of loops if I want to consider them algebraic. And I don't care about orientation, so I just record all of these 3 homotopy classes of loops that are represented by periodic orbits. And orbit equivalent flows have, well, the same set of 3 homotopy classes. I mean, you push forward the set of 3 homotopy classes, you get the other one out of the definition. The classification theorem program is to say that this is a complete invariant. And I write it as a program because the paper is not on the archive yet, but it should be soon. All right. So to conclude, we have a classification theorem for flows on 3 manifolds. And the whole toolkit is to look at a boundary at infinity. I realize I have 1 minute left, so I'll just cartoon this for you. If I take my flow, I can lift it to the universal cover. I can quotient orbits to points. I get some kind of space. Turns out it's homeomorphic to a plane. That's work of Barthelme and Frankel starting around 1995. And my fundamental group acts on this plane, preserving some foliations that came from my flow. And that action extends to a natural compactification by a boundary at infinity. So by studying the dynamics of this action of the group at the circle, on the boundary at infinity of this space, you can deduce that's a whole machinery for our classification theory for flows. I realize I've hit my time, and so I should stop. Thank you very much for your attention.
Thank you very much. Other questions?
In your theorem with Weisman, what happens if you don't have the barcode?
For the mapping class group? Yeah, so the whole mapping class group has too many finite but non-cyclic subgroups, so it doesn't act on the circle at all. But you can ask about finite index subgroups of the mapping class group and do they admit actions. There's no canonical candidate though for action of the mapping class group on the circle.
That's not the case. Let's thank you once again.